All right. Hello and welcome and good afternoon to everyone joining us. Thank you for joining us. We are putting on our first Composite Tech Talks powered by Composites One and IACMI. So today we will be discussing maximizing wind energy production with vacuum infusion. And we've brought in a very special guest, Ferruccio Baracchi, and we're very excited to hear from him. So we will wait a couple seconds though, because we are live right now. So we will let everyone drift in, but please feel free to type into the chat and interact with myself and the other hosts. Let us know where you're tuning in from today.
Also, let us know what you hope to learn in today's session.
Yeah, definitely. Make sure, let us know what we might talk about in the future that could keep you coming back. This is a series that we would like to keep on progressing, hitting on different areas of the composites industry. So any and all feedback is always welcome.
Yeah, since today's topic is focused on vacuum infusion, please let us know any questions you might have regarding infusion, and we'll hope to address those either during the presentation or towards the end.
Awesome, and there we go. Awesome, I'm starting to see the chat light up. So we got New Jersey, we've got Chicago. This is awesome. All right, so we're getting some good results right here. Kansas, welcome Kansas. All right, and one more time, we're really happy and excited to welcome you all to Composites Tech Talks, powered by Composites One and IACMI. Our first topic is going to be maximizing wind energy production with vacuum infusion. And to help us out and to give us some really good information, we've got James Jones. He is the lead technical support manager for Composites One. And we've got special guest Ferruccio Baracchi. He is the field technical assistance manager from Europe for Aerovac. And you've got myself. I'm Tyler Blevins. I'm the workforce and community development manager at iacme, the Composites Institute. So one more time, before I highlight our fantastic sponsors, I would love to hear from you all, the audience. And just one more time, put in this chat where you're coming from, where you're tuning in from today, and also any future topics you might like us to hit on. All right, and so I will go ahead and begin by introducing our sponsors for today's first episode. We've got Composites One, we've got iacme, the Composites Institute. We've also got Aerovac, MVP, that's Magnum Venus Products, as well as Closed Mold Alliance. So real quick, to give you an overview of iacme, the Composites Institute, we are committed to accelerating the development and adoption of innovative manufacturing technologies for low-cost, energy-efficient, advanced composites. Our collaborative work through partnerships with industry leaders like Composites One drives domestic production capacity, strengthens U.S. manufacturing competitiveness, and elevates job creation across the composites industry. And now I'd like to hand it over to my co-host, James Jones from Composites One.
Thanks, Tyler. Yeah, it looks like we have people joining from all over the world, really. We got Italy, awesome, and Utah, Canada, Kansas. Myself, I'm sitting in Texas right now. How about you, Tyler? Where are you joining from?
I am tuning in from Knoxville, Tennessee.
Yeah, and then Ferruccio is joining us from Montevideo, Italy. Again, my name is James Jones. I'm the lead technical support manager for Composites One. Composites One is the leading composite materials distributor in North America. We have more than 44 stocking locations, partnering with over 600 key suppliers, and we deliver more than 40,000 different products on our own fleet of trucks. I'm part of a team of 10 technical support managers located throughout North America. Our role is to guide composite manufacturers on the most appropriate products and process solutions for their specific applications. With our extensive partner network, It allows us to develop the right solution rather than being tied to a single solution for all applications. So as I mentioned, joining me today from Mondevi, Italy is Ferruccio Baracchi. Ferruccio has extensive experience with vacuum infusion process across many different industries. Ferruccio?
Yes, and welcome to everybody joined. So I'm Ferruccio Baracchi from Aerovac. Aerovac is one of the major distributors of process material worldwide. Historical brand created in the 60s, actually with 240 team member, location in UK, France, Italy, North and South America. We have a film manufacturing plant in Italy, kitting plants in Italy, France, USA. All process material sites are qualified AS 9100, sorry. We do have a soft and hard tooling production in France and a consumable aerospace engine overhaul and instrumentation for petrochemical analysis in UK. We have a global distribution partnership with Composites One for full line of process material, experience, technical support. We got a team in Europe and Far East, South and North America, ready to support our customer in the best application of our product. So, James, if you want to get back.
Sure. Ferruccio, before we move on, what are we looking at in the photo here?
Oh, sorry, yes. The picture here shows a blowing line for bagging film manufacturing. And this specific line is capable for blowing film up to something like 10 meter open wide, while our maximum capacity is up to 16 meter.
Okay, great. So let's go ahead and get back into wind energy. So looking at a wind turbine, there are three main components that are manufactured from composite materials. We have the blades, then we have the nacelles, which is the cover that covers up the machinery and the electrical turbine itself. And then we have the spinner, which is the nose cone of the rotor. So these components are made out of composite materials because composite materials have very high strength to weight ratios. And that enables the turbines to have very high efficiencies. And although these are lightweight, high strength materials, the sheer size of these wind turbines with rotor diameters over 200 meters results in composite material weights over 170 metric tons. For those of us in the US, that's 375,000 pounds. Wind turbine blades seem to grow longer every year. And that's because the amount of power harvested from the wind is based on the swept area of the rotor. So if we double the rotor diameter or increase the blade length 50%, that gives us a 4-time increase in power. In the early days, wind turbines, the blades were made from wood. As they became longer and the technology advanced, composites started gaining favor. The first composite blades were open molded, but infusion quickly gained traction. Some blades have been made from prepregs, but really vacuum infusion is the predominant process for producing wind turbine blades today. Modern wind turbine blades are growing, as I mentioned, they're growing longer, over 100 meters, as pictured in this blade on the screen. So over 350 feet long. They weigh up to 55 metric tons or 120,000 pounds. And that's about 60% fiberglass or carbon fiber, about 30% epoxy or polyester resin, and the rest of it is core material, adhesives, and hardware. As I mentioned before, the nacelles are also constructed with composites. And as the blades grow longer and the rotor diameters grow, and the power increases, the turbines increase in size. So the nacelle has to get bigger as well. These nacelles can be over 50 feet long and be over 12 feet high. And many of them are manufactured with the infusion process as well, because they can benefit from reduced emissions, more consistent, higher quality parts. For this talk, we're going to focus on blades, since the infusion concepts are basically the same for all the different parts. Wind blade shells are typically constructed in two halves. So if we look at this cross section, it would be split at the leading edge and the trailing edge, and it's molded in two different shells, if you will. And depending on where you are, we were discussing earlier what people call those, whether it's the pressure and suction or windward and leeward shells. It kind of depends where you are, what they're called. So the shape is fairly simple, but there's distinct laminate zones in the blade shell. So this blue area at the top is pretty solid unidirectional laminate because it bears most of the flap-wise bending stresses. So that might be made from unidirectional fiberglass or carbon fiber. Out on the aerodynamic portion of the blade shells, we don't have much strength. We need to resist buckling, have some stiffness, so we have fairly light laminates that are stiffened with core materials, be it balsa wood or PVC or PET foam. So yeah, I mentioned earlier that the blades were first made out of wood, so they're still made with wood today, even with the high technology. In some cases, spar caps and root sections will be molded in a separate process and included in the primary infusion. The shear webs are the vertical portions. These are molded in a separate process. They get bonded into one of the shells, and then the other shell is bonded to the top, and the assembly is closed. Some blades are actually infused in one shot using internal bladders. So the infusion process is especially suited for large structures because it gives the benefits of closed molding using just a single mold. Imagine the space requirements we would need if we had to have a two mold set, basically a counter mold. The blade factories, they're already very large. They would have to be twice the size they are today, and the output would still be the same. With infusion, rather than a rigid counter mold, we just use a thin vacuum film to seal the mold.
Yeah, and
as I mentioned before.
Go ahead,
James.
These let also handle the eventual undercuts that you may have in your shape, things that with a rigid mold is impossible to do or very difficult to do.
Right. Yeah. So if you have any negative features or negative draft, you can still get it out of the mold. So the reinforcements commonly used in wind blades are non-crimp unidirectional multi-axial fiberglass or even carbon fiber. As I mentioned, core materials are either end grain balsa wood or polymer foam. So in infusion, these are all loaded into the mold dry. So there's no resin. There might be some contact adhesives to hold everything into place while we place all the processed materials in the vacuum bag. So once the dry reinforcements are loaded into the mold, they're covered with a peel ply or a perforated release film. So as the name suggests, the peel ply can be peeled off the cured laminate. So this allows us to remove the processed materials, and it also gives us a nice textured surface for secondary bonding. The flow media is applied next. Since we're using very compact, high fiber content laminates, we need something to increase the laminate permeability, the ease with which the resin can flow through it. So we add a flow media that's fairly open construction that allows fast flow of the resin across the surface. As Ferruccio will talk about a little bit later, there's also some combination products where you can put some of these materials down in one step. So resin feed lines like this spiral tubing are strategically placed to distribute resin along the length of the blade, and then it can flow across the laminate towards the vacuum. So the vacuum line is placed around the perimeter to maintain full vacuum on the part throughout the infusion. And there are specialized connectors that connect the resin feed lines and the vacuums to our vacuum pump and to our resin source. And all these process materials are sealed onto the mold with a vacuum film that's sealed with a specialized sealant tape. Ferruccio, can you give us some more detail on some of the process materials that enable infusion?
Sure. So bagging film is a primary product needed for infusion, and we have production of bagging film concentrated in our northern Italy factory based in Mondovì, near Turin. Here we produce all the bagging film for the different application, not only for infusion in wind application, but also for aerospace and automotive autoclave molding, marine and wind energy infusion, as well as some of the release films. In wind infusion, typically we supply 3 different grades of multi-layer film. We got the Vacuum 400 yellow, Vacuum 465B, and Vacuum 850G. These are identified by different colors, yellow, blue, and green, mainly supplied in 75 micron thickness, even if other thickness are available and can be made, with different performances as per elongation and maximum application temperature. So to match the different working and environmental condition on the market. A quite clever way to provide the bagging film is in format. So format, they come, they come, as you can see from these drawings, in a way that are shaped, optimized to follow the specific blade, shell, or web dimension. The formats are made on a machine in a high moisture environment, packaged so to keep the moisture in the film, so to enhance the flexibility of the film itself. Advantages of formats are mainly related to film waste reduction, improved productivity, ease in handling, and just because you avoid the usage of crane to move the formats along the blade, as their weight is generally much lighter than a stock roll. Formats are tailor-made to the shell or web dimension.
Hey, Ferruccio, we have a question from the chat.
Yes.
So it's talking about the length of wind turbine blades and how fast they turn in a minute. Do you have any insight on that, or do you want me to take that one?
They run quite fast. The speed at the tip when they are rotating at average RPM can reach something like 250 kilometers per hour at the tip.
Okay, so Stephanie also had a follow-up. If it's a shorter blade, is it going to turn faster?
Yes, in principle, yes. But generally, the matter of fact is that there is not a very, very big difference in RPM. The difference is in the say the power that the blade is transferring to the electrical machine. So you have with the same rotating speed, you have a much higher power with a bigger blade, so you can move a much powerful machine, electric machine.
Okay. Thanks.
Awesome. Thanks, Ferruccio. And thanks, Stephanie.
No problem. So if you want to go back to the formats, the formats comes always from a lay flat tube roll onto which we do the nesting of 2 formats of the same dimension. Consequently, we will always have 50% of the formats that are wound up tip to root and 50% that are wound up root to tip. Once the format is has to be placed on the mold, the operation is extremely easy because, as I was saying before, format is very light, so 2 persons can hold the roll at the two extremity, and walking along the mold, they can position the format along the mold shape. And then the only operation they need to do is to cut. Maybe you can go to the next, yes, exactly, is to cut the side that is identified as side A. Once that is cut, you only need to unfold the format onto the mold and directly seal the bag on the flanges, on the technical flanges. You don't need to cut off anymore any excess of film. So you reduce your waste of material, and you avoid to carry on a somehow risky operation, handling with scissor or sharp knife around the bagging film that is sensitive to cuts.
Yeah, and let us know in the chat if anyone is using any of these formatted vacuum films today.
Absolutely, yes. It is a very, very, say, spreaded widely technology. We are already supplying formats in realty to major wind energy customers. So the other process material that are needed in the infusion of a wind blade are release film. Generally, the release film for wind infusion application are based on polyolefin, can vary in thickness, generally from 30 to 50 microns, and perforation. Perforation is important, as is the operation that lets the resin pass through the film and then infuse, penetrate, and saturate the laminate underneath. We have developed, there are a couple of different options in perforation. We have developed a specific pattern that is the P16 that grants the correct resin flow and maintain the structure of the film, so to be able to peel it off at the end of the process in a single piece, avoiding to peel it off in bits and pieces, so impacting on man hours, reducing the man hour needed for cleaning the part at the end of the infusion. So James, if you want to, okay. So other material that we have involved into the manufacturing of blades is peel ply. As James was mentioning before, peel ply is a porous, generally polyamide textile that is placed over the part underneath the infusion mesh, and it is used for generating on the part at the end of the process, peeling it off, as the name says. You generate a very clean and homogeneously rough surface ready for secondary bonding operation. Another important component is flow media that, as mentioned earlier, increases the laminate permeability, so it enables the resin to flow on the top of the part and then penetrate into the laminate. We have available different kind of flow media, from molded netting such as the VI10 or knitted mesh such as the VI1B. Sealant tape is also an important part of the job, because it's the material that grants the vacuum tightness between the mold and the vacuum bag. There are different sealant tape, different grade of sealant tape that differs in terms of tackiness at room temperature or maximum temperature withstanding. An improved application is also the possibility to have the sealant tape in a twin parallel format, so to improve the application time on the perimeter of flange. The release film and the flow mesh can be supplied also in a combined version. So we do have material where we combine perforated release film with knitted flow media, as well as perforated release film with molded flow media. An important part of the job that the combination material does is not only the fact that it's easier and faster to put in place, but also the fact that when you overlap a combined material, you are not perturbing any flow of the resin, because you always have the mesh between the two release films. While if you overlap simply the release film, perforated release film, it's very difficult that the holes will match. So you are generating a kind of stop for the resin flow that may perturbate the flow of the resin along the part. Then I think that is very much a very preliminary introduction to process material range.
Thanks, Ferruccio. Yeah, and if we look at a photo of a blade with all the process materials on, ready to be infused, you can see. So the green strips are the molded net flow media that's covering the solid skin portions, and so that allows the resin to flow across top and then down through the reinforcements. And then you can see the peel plot in this section where it's most likely covering a core. So in that area, they're using the grooves in the core as a flow media. So the resin flows through the grooves and then saturates they're fairly lightweight skins over the core materials from there. You can also see the resin feed lines going the length of the blade. They're set up in a sequential fashion. It flows out from the feed line. The further it flows, it begins to slow down. So we can basically restart the infusion with a new resin feed line. So we have the external hose that's connecting to our resin source, and these will be spaced at various distances along the length of the blade to supply the resin feed lines. The resin will flow out in both directions until it flows a little bit past the next feed line, and then that one will be opened. It'll flow to the next one, and that one will be opened, and it'll flow to the edge of the mold, filling up the part. Ferruccio mentioned before, you can also see there's a bonding flange that's being molded in this process that would be difficult to do if you had a rigid counter mold. So we can see the vacuum film on the mold, and it's sealed with 1 or 2 rows of sealant tape. In some cases, people will use a second bag to make sure that they don't have any vacuum leaks.
Yeah, a very peculiar product we have developed specifically for infusion and mainly for wind energy infusion is a microporous vacuum line, VMS3 or VMS4, that is available in various widths, with or without perforated release film on the surface in contact with the part. This product, positioned directly on the part in critical areas, is granting the optimum vacuum, avoiding dragging resin out into the vacuum hoses and giving a safe freedom of infusion network designing, avoiding dry spots, and it's useful in the area where the laminate transitions from solid to sandwich, or to grant the vacuum and correct impregnation onto solid insert, such as longitudinal reinforcing that can sometimes be made by already pre-polymerized pultruded sections. As you can see here, sorry?
We have a question about what the average gel time of resins used in this type of infusion.
Gel time, so consider that you have generally something like a 2-hour infusion time. So it takes 2 hours to more or less 2 hours to fulfill the part, and then from the end of the infusion to the peak, it may take something like 45, 50 minutes, something like that, to exotherm peak.
Okay. Okay. Thanks.
Is that satisfactory as answer?
Yeah, that's great. That's great. Yeah, so tell us a little bit more about the VMS3.
Yeah. So as I was mentioning, and you can see from this picture, this is a spar that is a very critical part. It's a solid, extremely thick part made out of unidirectionals. As you can see here, we have the resin infusion line on one side of the part. The vacuum is granted only by VMS3 that is positioned on the opposite side. And specifically here, we have the infusion flow media, so the mesh, that is positioned between the mold and the part, so to have an impregnation from bottom to top. As you can see, the flow front has got this peculiar shape, quite rounded. This is due to the fact that the part is, as I was saying, very thick at the center, and it is tapered at the end. So the thickness is diminishing at the ends and is going down to one layer. So where the layers are less and the content of glass is lighter, the resin impregnation is faster. So that's why you have this faster flow. But as you can see, at the end of the process, the part is, in this case, is almost completed, and it will be totally completed, as you can see in the next picture, the next slide. Yes, you can see that, first of all, there is no resin at all inside the microporous vacuum line. So the vacuum mesh is totally dry. So it means that you are not dragging out any resin from your system. And also from the video that you may see now, you can see that the part, first of all, is completely impregnated, totally saturated. The material, the VMS3, is extremely easy to release, and it is not leaving any remarkable print through on the part. So it's working in a very profitable way.
So at this point, we're happy to open it up for questions. So we've taken a few during the chat, but please go ahead and enter them into the chat, and we'll get to as many of them as we can.
Yeah, thanks, James, and thank you, Ferruccio. And one question that I did see come into the chat just a little bit ago from, I believe, I can't remember who it came in from, but I do have the question. It's, what is, on average, the increase in productivity achievable using pre-cut in blade manufacturing?
Sorry?
Yep, so one more time. So what is, on average, the increase in productivity achievable using pre-cut in blade manufacturing?
Yeah, the formatted bag film.
Yeah, I mean, it's difficult to evaluate. What you can evaluate easily is the advantage in terms of reduction of wastes, because that is a simple calculation of the saved square meter of glass. Related to, if you think about the timing, you have some advantages if you compare it with the usage of the roll stock, for instance, because you don't need to cut off the extra film from the shape of the blade. So you have a reduction of waste management too. Time-wise, there is some advantages, but is not the focus for formatting mainly. The focus is on reduction of waste, reduction of amount of film to be used, and ease of handling the format, not needing a crane, so not needing to stop your production, waiting for the crane to come, or acting, let's say, in a more simple way.
Awesome. Very well explained. Thank you. So another question we've had come in, could you explain how a large amount of resin can flow through a release film with very small perforations?
Yeah, I mean, the matter of fact is that the release film, the perforation of the release film is generating somehow, can generate somehow a break to the passage of the resin, but is not the most significant effect, because it is, in principle, the glass fiber itself that is generating the needed time for being saturated by resin. So it's not really impacting so much. The difference of perforation is generating a certain, say, variation in the saturation time, in the infusion time, but is not doubling it or multiplying by 3. It is just possibly, depending from the laminate, is possibly increasing it by, I don't know, 10%, maybe less than that.
Yeah, and I had a question just this morning, actually, from a customer about, it was almost the exact same question, and so they were saying if they were just to pour water onto the release film, that it wouldn't drain through very quickly. But I was reminding them that we're using the power of 1 atmosphere, basically full vacuum. So it would be like having 10 meters or 33 feet of water above that release film that's creating the pressure to push the resin through. So exactly. I mean, most people don't realize how strong vacuum is. I mean, you're talking about 100 kPa or almost 15 psi, which is a lot of pressure.
Yeah, that's the point. And we do have say, demonstrations of the different flow or the different timing for impregnate the same laminate on using 2 different pattern of perforation, and it came out that yes, even if there is a difference that is relatively small, but the major advantage is the facility of release. The fact that when you release the film doesn't break into bits and pieces, as it happened if you have got too much perforation. Let me use this wording.
Awesome, thanks. So we've had a couple more questions that actually flowed in. So I believe it's Danilola and Mares. They kind of asked a similar question. Basically, it was put to us, how often are the blades serviced once in operation? And also, what is the average life in service of the part? And to add on top of that, Mares asked about the residual stress that occurs within the blade and how you might minimize that amount.
Well, this second question, it is belonging to the say, the engineering and the structure of the blade itself, and is a little bit out of our control as provider of raw materials. It's more in the designer of the blade. For what is regarding this, how many the period where the blades are serviced, I would say that as far as we know, unless there has been an event that has somehow impacted with the blade, like something that has hit the blade or a thunder stroke or something like that, The blade itself is a quite robust material. It's a quite robust part, and it's lasting several years without a real need of servicing, unless occasionally some surface treatment for maybe refurbishing certain specific parts that are added after the infusion, like protection of the edges of the blade that are applied after the infusion.
Awesome, thanks, Ferruccio. So we've got another question that just popped in. So what resin viscosity is typically recommended or achievable for general
you tend
blade
not to
infusion?
go, yeah, generally you tend not to go higher than 120, 150 centipoise.
Yeah, it depends on the resin. Most blades are constructed from epoxy. Some are constructed from polyester. And generally, infusion polyester resins can have a lower viscosity than an epoxy. But as Ferruccio's saying, anywhere, I've seen them as low as 85 centipoise up to about 300. Getting above that, it gets very difficult to flow and saturate the materials.
There has been experience of infusion, not in the wind business, but into mainly railway parts, that has been infused with highly filled resins for fume and flame resistance. And this resin was extremely high in viscosity and extremely high in fillers. So the infusion strategy was completely different than the one that you may apply on blades. But at the end, it worked. And we were talking about something like 1,200 centipoise, possibly.
Wow. Okay.
Very impressive. Well, awesome. So we've got one final question. It looked like it came in from Jonathan, and he was asking about where he might be able to find a recording of this presentation. So answer to that is pay attention to the Composites One, the iacme, and the Aerovac LinkedIn pages. You should be able to find a recording of this exact episode right there on those pages. We also want to highlight our next Composites Tech Talk next month. We will be hosting Drew Simmons from Magnum Venus Products, and he will be discussing with us why the right equipment matters. So it's going to be a really cool discussion. I really hope you all tune in for that. And one more time, I would love to thank our sponsors for today. We've got Composites One, we've got iacme, the Composites Institute. Of course, we've got Aerovac, Magnum Venus Products, and Closed Mold Alliance. So on behalf of myself, Ferruccio, and James, we really want to thank you guys and hope to see you soon.
Thanks everyone.
Thanks, everybody.